I believe in the power of examples, so let's see what you do once you find a metric measure space on the street. The first thing you do is you look at the distance and ask if your space is path connected. If given any 2 points, there is a rectifiable curve connecting them. Is x quasi-convex? Is the length of the curves you find between x and y is comparable to the distance xy? Is that distance almost equal? Is the space length space, in other words? Is the space geodesic? Can you actually find a curve with length exactly equal to the distance of x to y? Then there are kind of topological properties. Is x complete? Is x locally compact? Is x proper, which is metric and topological? This requires that closed balls in the space be compact. So these are the metric properties of the space. Then it comes to measure. We ask if you have Borel regularity of the measure. We discussed this in 2 videos earlier. Is mu doubling? Can you bound the measure of twice the balls by measure of the ball? And is it alphas regular? Unfortunately, this is one notion that I did not mention in that video. This is just saying that there is some alpha, some power, so that the measures of balls of radius r is basically comparable to r to the power alpha. If you are alphas regular, then easily you can see that you are doubling, but the converse is not always true. Now you have your space with the metric and the measure. You can ask whether your space supports a p Poincare inequality for some p. And once we will learn about different classes of Sobolev functions, you can ask whether these classes are equal, they coincide, or is there strict inclusion? What is the behavior of Lipschitz functions on the space? Are they dense in the Sobolev space? And do you have Sobolev Poincare inequality? And many more questions. So before getting into details of the theory and defining everything, I thought examples will be very motivating. And let's, without further ado, look at some. Beginning with the simplest ones, you take a, say, open subset of some Euclidean space. The metric is just restriction of the Euclidean distance, and the measure is the restriction of the Lebesgue measure. So a ball in this space, so I will need these colors. A ball in this space either will be an honest Euclidean ball, or it will be only the part of the ball that lives inside your domain. So in this case, the ball will only contain this region here. You can still see that the measure is alphas regular, so measure of every ball at centered at some point in your space with radius r is well less than pi r squared. Well, this will be okay. Let's not be precise with the actual constant. So this is basically r to power n. It's at least 1/4 of the complete balls in the Euclidean space. So this is definitely alphas regular. This is Borel. So n alphas regular. It's a regular Borel measure also. How about the metric properties? So this space is definitely a geodesic space. Between every 2 points, there is a shortest path, shortest rectifiable curve, which is just a straight line parameterized the right way. Does this space support a Poincare? Yes, actually it supports the best Poincare that we can hope for, which is the 1-1 Poincare. Of course, this is not an easy fact, but if you believe in Poincare inequality in the Euclidean spaces, then this follows immediately for this space as well. So that was easy. Second example, we look at how about two copies of this at some distance from each other. It's one square 2, just the interiors. Now you see that the space is not path connected, so definitely it's not quasi-convex. The shortest path between these 2 points has infinite length. There is no such thing. It's infimum of empty set. But locally everything looks good. The measure is still Alfors regular, so the measure behaves quite nicely. By the way, here for this you need to put an upper bound on this r of say less than diameter of your space. In this case is omega. Of course, if you take very large diameter, this will be much larger than the measure actually you see. So in this case also you get that. But now we see that this Poincare inequality requires connectedness. We've mentioned this before. So it's a good instance to stop and recall what Poincare was. So you take a ball, you look at average of your function on the ball, and then you look at the oscillations of the function, and then you take integral. So you look at the average oscillations, and for P Poincare to hold, you need for the existence of a C, so that this C diameter B, then average integral of whatever notion, realistic notion of derivative of u you have to power P integrated 1 over P. So that means, does there exist some C so that we have this inequality for all balls in your space? And right. So balls in your space. By the way, so here I'm using balls in 2 meanings. So the honest balls in the Euclidean space, and also if you look at the ball inside this intrinsic balls in this metric space, they never, of course, go outside the space. Okay, so for all balls, and then, well, Poincare inequality, the only version we have defined is for all Lipschitz functions u defined on your space, and g in this case will be just this derivative of u absolute value, because in this case you're in a Euclidean space. The local Lipschitz constant here coincides with this norm of the gradient. Here we are in Euclidean space. There is an honest notion of derivative for Lipschitz functions by Rademacher's theorem, but all we need is just the norm of that, and that will be important in future, where you don't have a derivative, but then you have a notion of norm of derivative, some object that plays the role of the norm of derivative, which will often be denoted by g, and that will be called an upper gradient. But anyway, a Poincare inequality means an inequality of this type for a large class of functions. In our case now we said Lipschitz with their local Lipschitz constant. In future we will say, okay, continuous functions with upper gradient, and even more, if you require even more, we say all measurable functions with an upper gradient. And these are different actually Poincare inequalities. Some spaces support one type but not the other, and there are also theorems saying under which conditions, if you get it for Lipschitz class, which is the smallest, then you get it actually for all measurable and upper gradient pairs. But anyway, so let's see if on this space we could afford such a Poincare inequality. Does such an inequality require much of the space? And the answer is yes, because what you can do is you take some point x here, and then you take a ball of radius large enough so that you pick also something from there. Well, this is not the ball in my metric space, remember, but the ball is intersection of this with the space. So everything I'm trying to shade here is the ball. So of course a ball in a metric space doesn't really need to look anything like a round nice shape. So this is the metric ball, that this B here for this space. Now I will make the Poincare inequality fail. So the best I can do, and I will do, is that I take a function so that this side is exactly 0 and this side is non-zero, so there is no way, no choice of C will fix this. And to find such a function is quite simple. You take a function u to be some constant 1 on this piece, and then you take u to be a different constant on this other one. There is some restriction though because of Lipschitz. Okay, well, the Lipschitz constant will go up. So you can choose any C1 and C2, so you definitely choose them to be separate from one another. And now the local Lipschitz constant, or say this norm of gradient, is definitely 0 everywhere in this ball. So this integral will be 0. But then we'll average of B, depending on what volume ratio versus the C1 to C2 ratio you have, this will be some quantity, and whatever it is, this is not constant. So u cannot be equal to u, yeah, whatever this number is, u cannot be equal to that on this part and also on that part. In one of the parts at least, this will be a constant other than 0. So the integral will be at least the volume of that half times that constant. So you see that, interestingly, this, say, analytic inequality captures some metric property of the space, namely here that the space needs to be connected. Well, it seems like I also needed a good review of the Poincare inequalities that we wanted. So I was saying that in Euclidean space you have that. In a metric space you also allow for a bit larger ball on this side. So in some sources this has been previously called a weak Poincare inequality because you technically don't have the same ball, but you dilate it a bit on this side. So a Poincare inequality means there is a C and there is this lambda bigger than or equal to 1 where this happens. And in this case it wouldn't help anyway because of the same issue. Now I want to build up on previous example and then make things. Okay, why do we need this example? Will show us this dilation. Why do we need this dilation bigger than 1? And the example I have in mind is that, okay, remember that in the previous example my problem was connectivity. So what I do here now is I take this space and then I remove a segment. Okay. Now my space will be everything inside here. So this is the annulus, but only part of it. So this is my subset. So it's sitting inside Rn, R2 here. You can say that the boundary is not included or included. That doesn't matter. So when you move into the world of metric spaces, that really doesn't matter. This we regard as a set in itself. So it's open in itself, of course. So the distance is the restriction of the Euclidean distance. So distance of this and that is the length of this line between them. That will come in handy in a moment. And the measure is again just the restriction of L2 measure to this set. you can check that this is quasi-convex. So maybe let's write this down. It's not geodesic, as I showed the shortest curve doesn't exist always, but you can find path with reasonable length compared to the point. So the worst you have against the quasi-convexity is that these are pretty close. Their distance is this, but the shortest path is not as short. But anyway, if depending on this radius, given every x and every y, there exists some rectifiable path with length of this, say, less than 100 times the distance of x to y. So that makes it quasi-convex. Quasi-convex is a necessary condition for Poincare inequality, so this is moving in the right direction. Now, if I try to duplicate my previous example, let's see what happens. Again, I put a function that is some value here, some constant value, starts with some constant value around here, and starts with some different constant around this part. But, well, because you have a Lipschitz in particular continuous function, these values will come together. So let me actually make life simpler. Let's say your function starts with 0 here and ends with 1 here, and the increase in the function happens, you can require it to happen pretty. So increase from 0 to 1 occurs here. You can imagine that outside this portion, the function is still constant. So u0, u equal to 1, and so on. Now, if you take a ball which is centered at this point, and you take the radius this much, you will see that, again, u minus ub is non-zero. But this integral over the same ball of this gradient of u to power p 1 over p is 0. So no matter how big you take your constant c, you will not be able to make this happen. But we do have Poincare inequality on this space if we allow this help from lambda. In particular, but there exists some lambda large enough, maybe you will take it 100. So in that case, well, yeah, in that case, the ball, so maybe if you take it, let's just be safe, more than 200, then this lambda b, even if you take very small ball, so remember this happens when the radius of the ball you take is at least about this gap, and then we said that, okay, this annulus is kind of radius 100 relative to this. So even if you take the smallest ball, which touches both sides from here and here, it has diameter at least 1. And if you dilate it by 200 times, you definitely cover the whole annulus. And in particular, you capture this part where that gradient lives. Therefore, we do have Poincare inequality if we allow for dilation, or in the previous terminology I mentioned, we do have weak Poincare inequality. So diameter of b, then integral over lambda b, gradient u p 1 over p. So on such a nice space, it's basically just a rectangle but bent a little bit. You cannot afford to not have Poincare inequality. If this space did not support the Poincare, then what space will? Okay, the third example, and maybe let this be my last, because I had a lot of examples, but I don't want to rush and put them all in one video. If you like longer videos, let me know. So we want to make the situation worse. Remember this argument that I had that, well, lambda b should capture this other end here. And you can choose such a lambda because of this gap is something. It's not 0. What if it was 0? And this leads to the example of what they call slit disk, but actually I'd like the slit domain. I mean, sorry, slit annual is better. It's just a bit easier to visualize than the slit disk. So what is a slit disk? You remove just one line segment from this. So everything will be included except this line here. So this actually touches. Okay, so that is your x is just annulus minus 1 radius. Now, here's this delicate issue of what class of functions you want the Poincare inequality for. Lipschitz functions kind of jump over this because Lipschitz, remember, is a global property. So if you have x here and y here, the values of function at x and values at y must be near each other because dxy is small. So Lipschitz functions kind of forgive this gap and they just don't see it. They really see the full annulus. And indeed, we have Poincare inequality for Lipschitz class here. If we want to duplicate the previous example, you want to take a continuous function. So we can take a continuous or even C infinity function, but not Lipschitz. So the difference between so how could a function be C infinity and not Lipschitz? Because the derivative for Lipschitz is bounded, but derivative for C infinity can blow up. So the function 1 over x is definitely nice, but it's kind of Lipschitz functions are nicer because they also have control back over the derivative. Okay, so this you can imagine a function that is C infinity on x and has constant, why am I doing this? U is a C infinity function, and just like before, it starts with different constant values here. So U is basically 1 for some time on this side, and then it is equal to 0 for some length on this end. And now, well, then there is the transition, right? So there is this increase from 0 to 1 happening around here. So of course it's smoothly increasing. So gradient lives here. That is the only part where you connect these values of 0 to 1. Okay, now Poincare fails any P also for U. Given any C and any lambda bigger than or equal to 1. So if you want to say there is no Poincare, you want to say that no choice of C and lambda will make it work. So the difference here is exactly that you can now find much smaller balls. You can find a ball with radius so tiny, And touching both sides, we can find ball that has radius epsilon much smaller than 1 and centered on this radial well, technically you cannot put the center there, so let's not talk about center. Has radius this much and has almost 1/2 its volume to the left and 1/2 volume to the right of the removed segment. So definitely there is such ball, intrinsic ball in the space here, just the yellow one there. The ball actually also will have this segment also removed from the inside. Okay. And now we see that epsilon is so small that this prefix lambda is not enough, so that lambda b will still be contained in this set where gradient is actually 0, in the constant parts of the space. So you had your lambda, of course it has to be fixed once, and then it's so small that this radius is so small that if you lambda times dilate the ball, you are still not finding this part where gradient lives. So you're still in the constancy part. Then just like previous calculation, this integral of b of u minus u average small original ball is other than 0. It has value 1 on one side and 0 on one side, so this is actually proportional to about 1/2 of the volume of b. But this integral lambda b, even with the help of lambda, of the gradient of u to the p du 1 over p is 0. And we see here, you can put diameter b and then c. So c, of course, won't help. Okay, so given any c and lambda, there is a ball which fails the Poincare inequality. So space X does not support any Poincare for any p. I already mentioned that Poincare inequality does imply quasi-convexity of space. Let's repeat this picture and see that this space is indeed not quasi-convex. So this is basically my space, only the inside. Why is this not quasi-convex? For the same reason. So there are curves, there are points which are, for every epsilon positive, there exists curve of length. So there exists x and there exists y with distance of x to y equal to epsilon. But any gamma from x to y should happen within this, should make one loop at least, connect them, has length of gamma, let's say more than 10. So this 10 will depend on this radius here. So if this radius is 10, definitely the perimeter is at least 10. So the quasi-convexity constant, so quasi-convexity constant is at least 10 over epsilon. But this cannot happen. We can go to 0. We can find smaller and smaller one. And again, it explains the previous example that if you have any gap, you get quasi-convexity because there is this lower bound on epsilon. But with just one line segment removed, you don't run into that. And finally, hopefully finally, the slit disk that you will see a lot is the same example that I did with annulus, and I hope now you agree with me that the annulus is kind of simpler, is disk minus one radius. You don't remove the whole diameter because then also you lose connectivity. You want to keep connectivity but kill quasi-convexity. For the exact same reasons, there is no Poincare inequality for continuous functions. There is one for Lipschitz though. And the examples again, you build a ball that touches both sides and you put a function that has very different values on either side. So even just with simple subsets of Euclidean space, you can see that nice stuff happens, and you already can test the general theory by these toy examples. So okay, so I think this is a good start. Definitely I will continue with many more examples. I find them more fun. And once we are tired of examples, I can present to you a bit more general theory and more precise definitions and rigorous statements of theorems. Until then, have a great day and have a nice time.